Hello everyone, my name is Martin Lonsky. I'm from the University of Illinois at Urbana-Champaign, and in this presentation I'm going to talk about coupled Skyrmion breathing modes in synthetic antiferromagnets, which is a research work that has been published very recently in Physical Review B, so please take a look at that paper if you're interested in more details about this. And also I would like to draw your attention to an upcoming perspective article in APL Materials, where you can learn more about the dynamic excitations of chiral magnetic textures. I would like to start this presentation by giving a short introduction to spin eigenexcitations of magnetic skyrmions. In general, there exist three different resonance modes of a magnetic skyrmion that are called breathing and gyration modes. So for the first one, the so-called breathing mode, you need to apply an AC magnetic field out of the skyrmion plane with the correct frequency, which usually lies in the low gigahertz range. And what happens is that the skyrmion diameter oscillates periodically as a function of time, as shown here. If you apply the AC magnetic field in the skyrmion plane, you obtain these so-called gyration modes, where the skyrmion rotates around the center, either in a counterclockwise or in a clockwise manner, again as a function of time. These resonance modes have been predicted by Mochizuki in the year 2012, and in fact, only a few months later, the experimental detection has been reported where people have performed microwave absorption spectroscopy measurements, and indeed they have proven that these skyrmion resonance modes exist. Once again, I would like to mention that if you're interested in more details about this, please take a look at this recent review paper. I think that the majority of research work so far has been of theoretical nature, and many publications have presented micromagnetic simulations of these breathing modes, for example, in different geometries, such as this ferromagnetic nanodot you can see here, or for example, for a one-dimensional skyrmion lattice, which is actually very interesting for potential applications, because you can excite the breathing mode of this very first skyrmion here, and due to the magnetic coupling among the skyrmions, the breathing mode can propagate through this one-dimensional nanostrip, and thereby you can transmit information even without moving the skyrmions around through your sample. So this is a potential interesting application, I think. Here we're going to look at a different material system, namely synthetic antiferromagnets, where only at the beginning of this year by Albert Fair's group, it has been reported that even at room temperature, skyrmions can be stabilized experimentally in these synthetic antiferromagnets. And usually these systems are trilayers, where you have a ferromagnetic layer, a non-magnetic spacer layer, and another ferromagnetic layer, whereby the two ferromagnetic layers are coupled antiferromagnetically by means of an RKKY-like interaction. What we have done in our work is micromagnetic modeling of these systems. So I'm going to present very briefly the most important energy terms here and also the calculated ground states. As I've mentioned, we have this RKKY interaction between the ferromagnetic layers. The dynamics is described by the Landau-Lifshitz-Gilbert equation with the precession and the damping terms here on the right-hand side. We further assume an interfacial Dzialushinsky-Moria interaction. We apply DC and AC magnetic fields perpendicular to these planes here. And finally, we also assume a uniaxial perpendicular anisotropy for our systems. These are some typical modeling parameters we have used for our micromagnetic simulations with OOMF. And here I want to show you briefly a few ground states of the system. For the example of a DC magnetic field of 50 millitesla, you can see here the skyrmion diameters of the top and the bottom layer as a function of the antiferromagnetic coupling strength. And what is interesting is that at low coupling strength, the diameters of the two skyrmions are quite different because of the different competing micromagnetic energy terms, while at higher coupling strengths, the diameters are almost equal. So now that we know that skyrmions can indeed be a ground state of our system, we look at the dynamics. We excite the system by an out-of-plane AC magnetic field with a relatively high frequency of 100 gigahertz in order to resolve the different resonance modes. For that, we calculate the FFT of the spatially averaged Z component of the magnetization and plot it here as the power spectral density as a function of the frequency. And no matter if we look at both ferromagnetic layers at the same time or at the individual layers, we contain 8 different resonance modes, where also interaction between these modes and phase relationships are different, because basically we have a coupled harmonic oscillator system here that is comparable to classical mechanics, for example. To give you another overview of the different resonance modes, you can see here the resonance frequencies plotted as a function of the coupling strength. You can see that the modes occur in pairs of 2, which we'll discuss in a bit. And you can also see that you can nicely tune the resonance frequency by changing the antiferromagnetic coupling strength, which will be useful for future experiments, for example. But so far, we haven't really talked about the origin of those modes. And for that, I'm going to show you some temporal snapshots of the different resonances for a particular coupling strength that is given here. So the lowest lying mode is around 6 gigahertz. And you can see that both in the top and the bottom layer, the Z component of the magnetization basically changes within this ring-shaped structure. And it changes in both layers at the same time in phase. You can also see that here in the time-dependent plot of the magnetization. So that means that we have an in-phase breathing mode where the diameter increases and decreases for both skyrmions at the same time. While for the mode number 2 at 27 gigahertz, the opposite is the case. So we have an anti-phase breathing mode, while the diameter of the first skyrmion increases, the diameter of the second skyrmion will decrease, and vice versa. For the higher order modes, what we usually observed are hybridizations of the breathing modes with radial spin wave eigenmodes of the nanodisk, as you can see here. And now with these pictures, we already have an explanation why these modes occur in pairs, because every time we have an in-phase and an anti-phase version of the corresponding resonance modes here. To give you some further details about the micromagnetic simulations we have performed, I'm going to show you this slide here with these 2 diagrams where we vary the DC magnetic field and also the saturation magnetization. And you can see that the first 2 resonance modes, which are the in-phase and out or anti-phase breathing modes, have a totally different dependence on these magnetic parameters, which can be very useful for experiments or future devices, because the skyrmions give us a unique dynamic fingerprint, and thereby we could detect skyrmions and we could even extract the corresponding parameters from the measurements. What is also interesting is that if you vary the saturation magnetization in the different ferromagnetic layers, if you have a strong enough imbalance of this saturation magnetization, so you have a kind of a synthetic ferrimagnet, the radial symmetry is gone for the resonance modes, but instead we observe resonance modes that look like this. And this would be interesting to be studied, for example, by means of Brillouin light scattering experiments in the near future. So to summarize, we have observed in-phase and anti-phase breathing modes in the synthetic antiferromagnets in our simulation. We have compared it to a classical system of coupled harmonic oscillators. We have also seen that there is a very systematic dependence on different magnetic parameters like the magnetic field or the saturation magnetization, which gives us a unique dynamic fingerprint of skyrmions. And last but not least, I would like to remind you of these 2 papers where you can find more information if you're interested, but I'll also be happy to answer any questions. If you have them right now, you can also send them to me by email. And with that, I would like to thank you for your very kind attention. Thank you very much.